I will kind of not give you a systematic exploration of all this, but rather highlight some specific aspects that would caution drawing too much intuition from non-interacting systems. So the first one is the breakdown of topological boundary correspondence. So this is work by, I'll follow some simple example that's given by Titus. And now this is PRX 2016. Getting the latest stuff here. But it's been, actually, the effect has been known for a while. I think they have a nice model to talk about this. So, so we'll look at the simple driven system, which is defined on a square lattice. So I'll first draw a square lattice. And the driving is going in 5 steps. So this is a time-dependent Hamiltonian, which has some sort of 5, it does things in 5 intervals within this period t. Okay, so think of the system repeating that in this way. So we have sites here where electrons can live, and there are A sites and B sites, which are colored in light and dark. And there is, we should think of having some chemical potential or so that distinguishes between these two sites. So now step 1 to 4 is hopping amplitude that lets hop particles with probability 1 between these two sites. Okay, so that's the 1. I'll put the 1 down here. Hopping with. So if I turn on a hopping term between these two sites for just the right time, I can make sure that whenever I started out with a particle here, it will be here with the probability 1. Okay, and that's what I want to do. And of course, if it started out here, it will go up with probability 1. So in the first step, these bonds are going to be activated. Then in the second step, I want to activate these bonds. In the third step, these bonds. And in the fourth, these bonds. Okay, and step 5 is I'll put down some chemical potential, some random chemical potential that localizes all single particle states in the system. Step 5 is random. Okay, so let's think about what happens in this system. When I am an electron sitting on any given site, let's say I sit here. Okay. Then in the first step, I hop upwards with probability 1. In the second step, I hop over there with probability 1. In the third step, I go down. In the fourth step, I go right, and I stop where I started from. And that you can, convince yourself that this happens at everywhere, because even if I started from a black site, I would go up in the first step. Then there would be a 2 here. I would also go around. So no matter where I start, I'll do a counterclockwise circle on one plaquette. Then I put down this chemical potential, and boom, I'm just localized. Something special happens when I start off at a boundary site. So suppose that the system stops here. Okay, so there's no more sites here. What happens then? When I'm a black particle here, nothing happens in the first step. In the second step, I'll hop over here. In the third step, nothing happens. In the fourth step, I'll hop over here. Okay? So if I'm sitting on a boundary site, I'll just hop over by two sides. I don't do a circle. I actually don't end up where I started from. So this is a toy model for a system which supports chiral boundary modes, but due to the fact that I'm localizing all these states in the bulk in the process, there's actually no churn number in this system. So if now I don't analytically work through this, but I'll just give you how the phase diagram, or sorry, the energy spectrum looks on this slab geometry. So we have some momentum. This is like in the slab geometry, right? Only the momentum along the edge is conserved. And then we have this quasi-energy, let's say epsilon, that's only defined from 0 to omega. And what happens is that there is one edge mode going, say to the right on that edge. There's going to be another edge mode that goes to the. So the potential is just just some random potential, not necessarily the sublattice potential, but just some random disorder. And the purpose of the disorder is just to localize all the states in the bulk. I mean, like an Anderson insulator, or just put a massive amount of disorder, and then you cannot support the churn number anymore. Right? So there's one edge state that goes up to the right, and then on the other edge there's going to be an edge state that goes down to like that. And since there is a periodicity in this energy and momentum space, I can actually consistently, this is a consistent energy band structure for a Floquet system. It would not be a consistent energy band structure for a periodic system if it was not a Floquet system, because I would not identify this point these four corners would not be identified otherwise, right? You cannot have just a state that goes up, needs to come down, right? This is fermion doubling theorem. Okay, now we have these bulk bands also sitting here somewhere. And these bulk bands are actually carrying churn number 0, as I said. So what you have here, in summary, is you have chiral edge modes, and you have bulk churn number 0 bands. And that is something you cannot have without drive. So this is peculiar to a Floquet system. So that's just to demonstrate that the bulk boundary correspondence is not there anymore. In the same sense we learn it for undriven systems. Okay. Now, the next 2 points I'll just mention in words. You have to think about not only the eigenstates of this unitary operator of the Floquet unitary, but if you want to really describe an actual physical system, you also have to think about if you want to end up in a desired phase, how you're going to initialize this phase starting from, typically like an undriven system, right? You want to switch on the drive at one point. And there can be substantial problems with this. It's a non-trivial, I'm not going to go into any detail, but there can be situations occurring where this initialization or where getting into a steady state that you want is not so easy. Let me just cite a result from Luca D'Alessio. This is Nature.com from 2015. So if I start in a churn number 0 ground state in a time-independent system, and I switch on whatever type of drive, then what he found is that I cannot change the churn number of this state, whatever I do, as long as the system is non-interacting and translational invariant. And infinite, I guess. I'm not sure whether this is actually required, yeah, probably. That's just the limit in which he was able to prove that this could maybe be extended to other situations, but it's just like to put up a warning sign that you cannot necessarily, even though your Floquet Hamiltonian might support bands with a churn number, the actual, if you actually compute the whole conductivity of your steady state, it might not at all have a churn number, even though you think you'd drive it in this direction. So this is just again to be sure that there is a distinction still between the physical state that you can drive a system in and the actual eigenstates of that unitary. And let me see, should actually, maybe in the interest of time, I'll not tell you about coupling to a bath. So I'll go from B to D. And it actually is even more consistent because I said we're not going to talk about coupling to a bath. And this is here I want to now mention some developments about interacting Floquet systems, which are recent and I think very exciting. So so far we've been talking about non-interacting band structures, and the reason why we wanted to talk about non-interacting band structures, so there's two things. I'll talk about pre-thermalization first. So the reason why we wanted to talk about non-interacting band structures is that we have a well-defined way of doing this high-frequency expansion. So this expansion can only converge, or is only shown to converge, if my time-dependent Hamiltonian is times the driving time, the period time, and this is a measure. This is some some measure, some norm that you can choose. I mean, typically like the energy of the largest energy of your system is small or equal to some order 1 number. Okay, so then this high frequency series converges, is guaranteed to converge. But again, in a driven many-body system, this is never going to be fulfilled, because if the system at least is thermodynamically large, there's no way the Hamiltonian can be bounded from above. Okay? So one way out of this problem, which would tell me that for generic systems, when I drive it for a long time, it will heat up to infinity. One way out of this problem is the concept of pre-thermalization. So this is actually probably Dima Abanin is the one to be credited with this. I guess 2015, 16, bunch of papers. So the idea here is that there is an exponentially long time scale over which the system actually looks like a thermal system. When I drive to infinite times, the thing will explode. It's going to heat up to infinity. I'm sure about that. But before I'm reaching this infinity, there is a long time scale where I can actually look at the system as if it was thermal. So to make this a bit more formal, we say that there is a time T star, which is of the order of some constant times omega over h, where h now is a quantity that is not the norm of the Hamiltonian itself, but it's the norm of any local term in the Hamiltonian. So instead of taking, of course, again, in the many-body Hilbert space, I have a problem because the Hamiltonian itself doesn't have a norm. But if I look at the local term, this is, of course, bounded. Like, for example, if you have a Hubbard interaction, you have the occupation, like n up times n down, for example, the occupation of a single orbital. This can never exceed 2 times u, say. So a bound for this would be u if you have a Hubbard-type model, and so on. So this is a reasonable quantity even in a many-body system. And then we have a time scale which is exponentially long in the frequency over just this local term measure of the system. And over these time scales, so 4 times t less than this t star, there exists a quasi-local and also quasi-conserved. Now you see I'm using quasi because there's some estimates going into this. Hamiltonian type quantity h star, such that maybe I should continue writing here, such that expectation values of a local operator, so if I have a state psi of t and some local operator O, they actually look thermal with respect to this Hamiltonian. So that means that I can compute them as the trace over some density matrix, let me call rho star times O, where rho star is proportional to the exponential of this h star over some effective temperature. And this effective temperature is given by the density, energy density of the initial state. Alex?
The question goes back to A.
Sure.
So I understand that there is no channel.
Mm-hmm. That there is no Chern number because all the states are localized. The eigenstates are localized, so I cannot, I mean, you need, to support a Chern number, you need Wannier states which are exponentially long and so on. Which are...
Generic topological simulator friendly.
Mm-hmm. But wait, not the Chern insulator.
No, I mean, right.
This is a Chern insulator. Yeah, I'm not saying that, okay, so this is not a counterexample against, now you're drawing it to another system, right? So I don't know. Yeah, there is one, I mean, there would be one guy, that's delocalized, right, in the lambda level.
But the argument will not work for winding number.
Yes, I think, I mean, okay, I don't know whether there is anyone who has constructed a winding, a counterexample to a winding number type. Yeah, no, probably this would not work, yeah. Maybe it's not 100% clear from just what I said in words, but if you do numerics, you use. There is numerics, which is a PRX. They have like done a lot, but yeah, no, you can. I mean, you can give the model explicitly, so you can compute the Chern number of the band if you want. Yes, yeah. Actually, this goes back to work from Kitagawa 2012, where they have already observed this in a classification type paper. So this is more like an explicit model for this observation back in 2012. What? That's also true, yeah. That's right. Yeah, very good point. Yeah. Yeah, maybe that's also a good way to rephrase why this is a Floquet property, because if you have a bounded system where you don't have this periodicity in omega, you know that if you go over all bands, the Chern number needs to be trivial, right? Because then it's just, the projector on all bands is the identity, so it has a trivial winding. But here I get around this problem because my upper band, there is still an edge state above the upper band, quote unquote, which can never be there in a full system. Yeah, thanks for that. Sorry, wait, what's what? Yeah, pre-thermalization is that thing that I'm explaining. So is that there is an exponentially long time for which, and that's what I was about to say, for which the expectation values of local operators look like thermal with respect to some effective Hamiltonian that's actually local. Well, but you see, the frequency of the light is like huge compared to the gap that we are opening, right? It, yeah, still absorbs, yeah. Okay. Now, that's that about pre-thermalization. And now, as a last point, I'd like to go to something that sounds quite fancy and has come up quite recently, and that's Floquet time crystals. And these are also intrinsically interacting systems. And the question here goes actually back to some work by Wilczek in 2012, who proposed the concept of a time crystal, which it would be, in his view, a ground state of a system that spontaneously breaks the translation invariance not in space but in time. Okay, sounds interesting. Many people were interested and inspired by this idea. Turns out it was wrong. It was plain wrong. The Oshikawa proved later that this cannot exist as a ground state property, but it was still inspiring enough so that people kept, sticking to this idea. And now, in the context of driven systems, where we don't think about ground states anymore, this came back. And the question that we now ask is changing a little bit, namely, can we have a spontaneous breaking of time translation invariance? So the Hamiltonian that we have in these systems is invariant under this shift of time by capital T, and we can ask, do all the properties of the system, when we look at the system, do they also need to be invariant under this shift in capital T, or maybe not? And now we know that this can indeed be the case, that there is a spontaneous breaking of the symmetry. So let me first give a definition of a spontaneous breaking of time translation symmetry. This goes back to very recent work by Else, so I'll choose the definition that Else et al. In their 2016 paper, I think it's not yet published, use. So spontaneous time translation symmetry breaking is the following. For all short range correlated states. Okay, so yeah, I guess I don't need to explain in mathematical words what short range correlated means. So let me call such a state psi of t. There exists an operator, local observable, let me call O again, so that when I look at this psi at t plus capital T and compute this observable, the result is different from when I compute it at t. Okay? And of course, between t and capital T, I evolve this state with the unitary of my driven system, okay? So that's the point. It's a statement, of course, about the type of driving that I use to get from T to T plus capital T. So, can we, the idea would now be to think about a simple realization where such a thing occurs. And again, we need interactions as for spontaneous symmetry breaking in conventional systems. So there comes the problem with our heating. So how can we get around this? And that might be a bit of a stretch now for you, but what we want to resort on is systems which do not obey the eigenstate thermalization hypothesis, which are not thermalizing states. And there is a class of such states that is known and is called many-body localized MBL phases. So these are phases which are interacting, but if you wish, they do remember for infinite times the properties of the initialization or the initialized state. So when I initialize in an MBL system a state with some charge that's maybe in a puddle somewhere, for infinite times this charge will stay put, even though I'm not, in an eigenstate necessarily of the system, for example. So MBL means basically that there is it's a non-thermalizing system, localized, and interacting system. Okay, now that's shouldn't bother you too much if you haven't heard about that at this point, because I'll just give you a Hamiltonian, and from now on you should just think of this Hamiltonian as being something that's interacting, but it doesn't heat up because of this property. And the Hamiltonian that I want to look at looks like that. Sorry. Okay, so I have spins that are on a one-dimensional chain, and these spins spin 1/2, right? And they interact with this sigma set terms, neighboring spins, and there is a random coefficient in front of this interaction term that depends on the site. And also I have a field that's pointing in the z direction with also random coefficients that depend on the site. And then I also could add a transverse field if I want to. Okay, so that's the system. It will have this, if I choose this randomness strong enough, it will be in this many-body localized state. And now I want to use this to construct a unitary operation, like a unitary that is the Floquet unitary of the system. Namely, I will, for some times t0, I will basically evolve the system with this MBL state. Actually, I'll choose it for hx equal to 0. I'll choose hx equal to 0, so I only have these sigma c terms. That's one part of my unitary, and the second part of my unitary is much simpler. It's just the sum over all sigma x operators on all sides switched on for a specific period of time. And that period of time is chosen such that, this exponential here is really just the sum over I sigma x for all sides. So what it does is it flips all the spins, right? So if I think in the sigma z basis, I exactly flip the spin on every side in this step. Okay, what do I do in this step? Well, I act with this Hamiltonian. So maybe it's convenient to think about the eigen states of this Hamiltonian and then do this flipping operation after. So if I go to this hx equal to 0 limit, that Hamiltonian has actually a nice property that I can enumerate all the eigenstates, or I can, diagonalize it kind of immediately. by just thinking about the spins in the sigma set basis. So when I look at the specific configuration of sigma set spins, so I'll just call the eigenvalue Si, which can take eigenvalue plus or minus 1 on every side, then this Hamiltonian is the sum, or the energy of such an eigenstate is the sum of these two terms. And you can already guess why I call these terms E plus and E minus. So E plus is going to be the sum over I, J, I, Si plus 1. No, Si plus 1. Yeah, it doesn't matter. And this E minus is going to be the sum over I, H, I, Si. So H, I, Z, Si. So you see these are these two terms in the Hamiltonian. Clear that this is the energy of them in a specific spin configuration. And this I call E plus because under inversion of all the spins, this energy stays the same, while this one changes sign when I flip all the spins. Okay, so knowing this, I can now actually write down the eigenstates and eigenvalues of the unitary. So for such a spin configuration Si, there are two eigenstates of the unitary, which have eigenvalues plus or minus e to the I t naught times e plus. I'll not put the Si configuration. It's clear that I mean that. And these eigenstates, you can convince yourself, are given by something rather simple, e to the I t naught e minus over 2 Si plus or minus to the minus I t naught e minus over 2 times Si. Okay. So, is that roughly clear why these are the eigenstates? So think about acting first with this spin flipping operation. Sorry, there should be a minus here. So this is the flipped configuration, right? So flipping the spins would map this one into this one and vice versa. And then you apply the MBL Hamiltonian, and you see that this E plus is the same for both, and the other ones get this relative minus sign in the E minus. So if you stare at it for a moment, you will see that this is indeed an eigenstate of that unitary. So we have completely diagonalized this unitary. If we look at our, let's think about these eigenstates for a moment. Do you think that they are short-range correlated? Who thinks that they are short-range correlated? Why are they not? Okay. Okay. Why are they long-range correlated? Think about a ferromagnet, right? So what are the eigenstates of an Ising ferromagnet? That system is, of course, time reversal symmetric, but breaks spontaneously to time reversal symmetry. So an eigenstate that explicitly is time reversal symmetric would be something like this, right? Now, is this a physical state of the system? Is it a short-range correlated state? No, right? I mean, no system looks like that, right? This state would immediately decohere if you put a local perturbation. There is like, this state would, if you compute the correlator between a spin over here and the spin on the other end of the system, it's not physical, right? What is the physical state is one half of that. It's not the cat state, but it's just all spins up or all spins down. And here is the completely analogous thing, just that we have now a given, we lay down some spin configuration on the whole system and we invert it. So this is not the physical short-range correlated state of the system. Each of these parts is one, okay? And if I turn this argument around, then I can look back into my definition of spontaneous time reversal symmetry, spontaneous time translation symmetry breaking. if I have a short-range correlated state, and I want to decompose it into the eigenstates of this unitary, which all have generically different eigenvalues, I have to use many of these things, right? I have to use many of these eigenstates of the unitary. Okay, so, and then, since these states have different eigenvalues generically, I have already one observable, my Hamiltonian, that changes as a function of time when I change my period by t. So basically, this means that this system does not, it does break spontaneously the time translational symmetry, because all the eigenstates of the Floquet unitary are not short-range correlated, or if I think about it in the reverse way, every short-range correlated state has to be sort of decomposed into eigenstates with different eigenvalue in the short-range, in the Floquet unitary.
Where did you use the fact that it's many variable?
This is implicitly used to say that the system doesn't heat up. Yeah. This is just, I mean, basically thinking of for this whole class of interacting systems, Floquet systems, to think about a long-term behavior in a reasonable way, you actually always want to use many-body localized systems. So for example, some effort is now put into classifying the topological or spontaneous symmetry breaking phases of Floquet unitaries, and then you would always only look at systems which are actually many-body localized, because otherwise it doesn't physically ever make sense, or it's not a phase that you would observe in a system in a steady state for a long time. Actually, this plus minus here, there is so you see the spectral pairing between two states that are shifted by a phase of pi. This is actually a way to classify, or this is related to a way to classify Floquet unitaries beyond the phases of the non-interacting systems. Of course, you can realize in a driven system any Hamiltonian with a classification of non-interacting systems, but there is an extra classification on top of that, and that is related to this spectral pairing of eigenstates or spectral pairing of eigenstates in the Floquet unitary. Okay, now I have only a few minutes left, but I showed you that now that a lot of things can go wrong when you think about driven systems and Floquet systems, and that would be great if you remove that thing. So I just want to show you that at least for non-interacting systems, it's actually not that bad of a description, and a lot of progress has been made in experiments in recent years. So I'll just flash a few of them. So the first one is really connected to this graphene type driven system with circularly polarized light. Now, because graphene is not that fancy of a material anymore, people decided to go for topological insulator surface states and shine. So this is work by Neupert at MIT. So what he did is he took this topological insulator surface state and irradiated it with circularly polarized light, and he wanted to observe this Floquet band structure. So the way he does it is with a pump probe experiment. So you shine this intense light pulse in for some not that long period of time, actually, even though you think about periodically driving it, but anyways. And then you probe it with another probe pulse, and you do an angle-resolved photoemission spectroscopy experiment with this probe pulse. And what you see with loving eyes is that Dirac cone replicates, and there are hybridization gaps opening between these different Dirac cones, which would be our Chern number, our sigma z gaps. And this is from Science 2013. Now, here you see, again, this a bit clearer maybe. You see this is the Dirac cone. This is with circularly polarized light, and there is a small gap that he calls 2 kappa, which is opening at the Dirac point. Here, this is with linearly polarized light, and well, it doesn't look as clean, but certainly also not as much as like a gap system. In the meantime, they improved their setup, and this is a paper, I guess, from this year. Yeah, Nature Physics 16. So this looks much better already, but it's essentially the same thing. And you see clearly all these replicas, and then if you analyze the data, maybe not on a color plot, but with the real data, you can map out this gap. And for example, you can extract the dependence of the gap to delta on the pump power. So what's the pump power? The pump power, well, I mean, this is the intensity of the light that you shine on. And this is now in a limit where A, the driving is strong. So if you remember, we had the square root of A squared plus omega squared. So this, if we are not in the limit where A is small, this is going to go proportional to A, right? And so it's, say, for example, the strength of the electric field. And this is going to be the power or the intensity of the light to the power 1/2, right? So that's what you would expect from Floquet theory. And that's what they find. So this fit here is power to the 1/2, the root of the power. And if it was linear, then it would have been this dashed line. So you see nicely that this relation, I mean, our exact result that we obtained with the Dirac thing is actually working in practice.
Where does the frequency of light stand with respect to the separation?
It's large, but I don't know how large it is. Well, oh no, you see it here. It must be the separation of these two things. So maybe 200 mid-infrared. I don't know what that means. Okay. Here is another experiment. Completely different setup, not condensed matter, but cold atoms. This has been done in the group of Tillman Esslinger at ETH. And what they wanted to do is they wanted to actually build a churn insulator. Now, building a churn insulator, you know, from the idea of producing this Haldane gap in graphene, this is not so easy. So if you want to do it in a static system, so really Floquet theory is here a tool to create the right mass gap that you want, the churn mass gap. And so the way they do it is that they put cold atoms down in a static, first in a static optical lattice, and they make it some sort of honeycomb lattice. They call it a brick wall lattice because it's not really hexagonal, but anyways, it sort of realizes this band structure that you want with Dirac cones. And then this is, of course, constructed by interference of light beams, like they are back reflected at some mirror. And then you drive this mirror with a piezo crystal so that it vibrates. So you shake your lattice, and you have this piezo crystal in the x and y direction, and you can shake these two out of phase, right? You can have a pi-half phase shift between them. And then it turns out that this driving of so if you shake the crystal structure, or the sort of the lattice potential in this circular way, you are actually really driving this Haldane gap in your Dirac system. And you open a gap, and then they can even map out different cases for the churn number. So they can basically see if you make a wave packet, and you see how this with a well-defined momentum near this Dirac point, you can ask how is this wave packet deflected, and this will tell you about the local Berry curvature in K space. So you can distinguish the case where the Berry curvature has the same sign on both Dirac cones, and the case where the Berry curvature has opposite sign between the two Dirac cones. So the two cases that I had down here with the staggered sublattice mass and the Haldane mass. So they mapped that out nicely. And lastly, this is another experiment in a similar spirit. This is from Emmanuel Bloch's group, also called atoms. But here they don't really build the churn. They also want to build a churn insulator, but they don't really use this thinking of driving a Dirac system. Rather, what they put down is a Hofstadter model. So it's like a super high magnetic field analog of a lattice model with a super high magnetic field. In this case, it's a quarter of a magnetic flux quantum per unit, per plaquette of a square lattice. And the way they do it is that they first put down some sort of staggered potential on this lattice. So you see these wells are lower and higher. And then you come with a bunch of laser beams which are cleverly arranged with their relative phase and so on. And you basically induce a Floquet part of your Hamiltonian that just overcomes this barrier so that the driven system, the hoppings acquire the appropriate phase so that you get this pattern of fluxes, and also then the wells are all equally deep, so you get some periodic square lattice structure. And then, depending on all these parameters and so on, they can tune between topological and non-topological regimes, and they can map out the Chern number really and see, again, by the drift of the atom clouds, whether you have this chirality in the system, and you can actually even quantitatively measure the Chern number in this system under some assumptions. Okay, good. So that's it. I'm out of time, and I hope that you are not too pessimistic now about Floquet systems. After telling you that a lot of things don't work, it's just much more richer than the non-interacting part. And a lot of experiments are actually underway in these cold atom systems in particular, so I think it's a quite exciting field. Yeah, so thanks for your attention. Do you have more questions? Or if you want to clap, you can also clap, and then we do questions. But so what I wanted to say when I said it's not physical, I mean that it is not, you should not think of it as an analog of an equilibrium Hamiltonian for some system. That doesn't need to be the case. Of course, it's still the tool to describe the system for us, but we just need to keep in mind that it's not a local operator. So that's all I wanted to say. And of course, you see that what we derived here are, in the non-interacting cases, are local operators when we looked at the Chern insulator. So this one is actually, that has not the problem. Exactly, yeah. When we have this expansion works, then we can trust it. This warning sign is more for these interacting cases where things might become like generically and like non-local operator. Yeah. So there, this doesn't hold any.
I also like, as a follow-up, try to understand when not there's this Floquet theory help. So particularly, let me ask for a quick example, which is this photo-induced anomalous solid effect in OS2.
Mm-hmm.
So the idea is that you shine certain polarized light. System breaks inversion symmetry so that it has local equal and opposite Berry curvature. Whole effect because Berry curvature adds up to 0.
Mm-hmm.
And you come in with a certain polarized light, and it's polarized in one sense.
Right.
It's just selected.
There is a selection rule, right? There is a p, like a 1/2 and a
Right.
-1/2.
So, for example, would this be a problem where Floquet helps?
Yeah. In the same way as for the Dirac. I mean, I again assume that you can. So first, it's non-interacting. You're probably driving with a high frequency compared to the band structure, or at least the portion that you're interested in. Like the portion. I mean, of course, like maybe far away from the Dirac or gap Dirac point, there's other energy scales, but the relevant part where you change occupation and so on is just that Dirac point. So I think you can work with a high frequency expansion there. So yes, that should be a system where this perfectly applies. Yeah. Thanks.